When a gas valve opens, something has to reach the temperature of open flame in seconds. No pilot light, no spark, just a surface that climbs past 1,000 degrees on demand and lights the gas the instant it flows. A silicon carbide igniter is that surface. A semiconducting ceramic that turns electric current straight into glowing heat, then shrugs off the flame it just started and does it again on the next cycle. Recrystallized silicon carbide is a semiconductor, not an insulator, so a voltage across the two tines drives a current straight through the ceramic and the material heats itself from the inside. Doping the lattice with nitrogen during firing sets how freely that current flows, which fixes the resistance the element will run at. Each cycle slams the surface from room temperature to around 1,400 degrees and back, and silicon carbide takes that shock without cracking. A thin, self-renewing oxide skin forms as it glows, which slows further oxidation, the reason the element survives thousands of ignitions instead of burning away. Its high thermal conductivity carries heat quickly into the hot zone so the tip reaches ignition temperature fast, while the cooler ends stay stable where the metallized leads are embedded. That split, blazing at the tip, steady at the base, is what lets a brittle ceramic carry both current and flame without failing at the joint. The physics is Joule heating, power equals voltage squared divided by resistance, so at a fixed line voltage the heat a given element makes is set entirely by its resistance. And resistance follows the geometry, it rises with the length of the current path and falls as the cross-section grows, which is why the hot zone is a long, narrow slot folded between two tines. That is why each element is slotted to a target. The slot between the tines is lengthened until the room temperature resistance lands in a set band, commonly 40 to 100 ohms. So that at line voltage the hot zone reaches ignition temperature within about 17 seconds, every unit alike. The last requirement is that the resistance holds steady over time. Because a recrystallized, nitrogen-doped body oxidizes so slowly, its resistance drifts only a few % across thousands of cycles, so the same element still reaches temperature in the same seconds after years of daily ignitions. An igniter's form follows the appliance it lights. Lead lengths commonly run from around 5 to 9 inches to reach from the control to the burner. The mounting tab and bracket are shaped to the manifold, and the hot zone comes flat or spiral depending on where the flame must be caught. Beyond the outline, the electrical target drives the design. The resistance band is chosen for the supply voltage, nominal 120 volts, with some systems stepping higher line voltage down to it. And the connector, pin style, insulation rating, and mounting tab are matched to the appliance so the element drops straight into the ignition circuit it will serve. Set at the edge of a gas burner in a furnace, boiler, or water heater, the igniter carries the whole ignition on its own. When the call for heat arrives, current flows and the hot zone climbs to around 1,400 degrees within roughly 17 seconds. The gas valve opens, and the fuel crossing that glowing surface lights at once. No pilot flame burning fuel around the clock, and no spark that can fail to catch. Because the resistance barely drifts, the element reaches the same temperature in the same time on the first cold morning and thousands of ignitions later. Between cycles the surface cools and waits, ready to repeat the climb on the next call for heat, season after season. The oxidation resistance that protects the hot zone is what turns a brittle ceramic into a part that lights a burner thousands of times without losing a step. Instantly, one small glowing blade replaces the standing pilot and the spark alike, the quiet starter behind the heat in a gas appliance.